20 to 30 years from now, we can expect our delivered packages to arrive in less than 30 minutes. We predict this will be accomplished through autonomous unmanned aerial vehicle deliveries, or AUAV deliveries, using the low-altitude, high-density intercity airspace. Before such a service becomes reality, the risk for UAV on UAV collisions must be mitigated. Even now, it is difficult to guarantee the safety of autonomous UAV operations, as exemplified by the numerous UAV on infrastructure and UAV on aircraft incidents. Because of these various safety issues, governmental agencies have become very conservative in relaxing safety standards and regulations for AUAVs. In spite of these restrictions, individual companies are still investing in UAV technology. However, without a coordinated technological framework to guarantee safety, the vision of the future of package delivery will not be realized. To address this issue, we have designed an air traffic controller for AUAVs that serve as a common platform for all AUAV operations within the intercity airspace. Our technology bridges the gap between government, companies, and consumers. Our solution is unique in its approach to solving UAV on UAV collisions. Inspired by commercial air traffic control, we adopt a similar centralized framework. Companies dispatch AUAVs with set trajectories to complete a specific mission, much like how airlines dispatch flights. In both cases, tactical separation is handled by the air traffic controllers. Human air traffic controllers for AUAV operations are infeasible. Hence, our control modules act as autonomous air traffic controllers, ensuring safety within the intercity airspace. Our system can be broken down into two main technological components, along with system testing, standards compliance, and ethical concerns. The hardware and embedded systems cover the physical AUAVs, onboard actuators and sensors, as well as the hardware communication interface. The software and algorithms include the server-based communication interface, as well as the core of the reservation system. In order to ensure safety and comply with federal autonomous UAV regulations, we used the UAV safety net at Pinovation Works. In the safety net, we marked out landing and takeoff locations for our two UAVs, as well as planned a conflicting trajectory through the middle of a reservation airspace. This mimics what would occur in the low-altitude, high-density intercity airspace. During testing, we monitored the health of both UAVs through a Q ground controller. Furthermore, two screens also depict the Odroid Mavros uplink, through which we allow our reservation software and the relay server to communicate with onboard computing. Finally, a screen depicts the output of our relay server and reservation system to ensure that traffic management initiatives are being upheld. The hexacopter takes off in the lower right-hand side of the screen. We have assigned conflicting trajectories to the hexacopter and the quadcopter. The takeoff location of the quadcopter is not in the frame. As you can see here, the quadcopter, because it was able to transmit its reservation ahead of time, before the hexacopter, the quadcopter was able to pass through the airspace first, whereas the hexacopter holds and waits for the airspace to clear. Once the airspace clears, the hexacopter also continues on its trajectory. This video sequence shows the successful traffic management actions taken by our control module and prevented a mid-air collision between the hexacopter and the quadcopter. Eagle Eye is an infrastructure for the future of autonomous UAVs. From the simple to interface hardware components to the adaptive software reservation system, our product can open any and all urban airspaces to new industries and innovation. Most importantly, it opens these airspaces with the guarantee of reliability and safety.